Hello. Okay, let me start sharing. I realized I stopped sharing my screen. So, at any point during the lesson, if you have any questions, please feel free to either, I'll just say hello here, type here in response to that message, or go ahead and speak up so I can hear you. Okay? So let me just check and see who's here. Oh, Rocio, how you doing? Are you signed on yet? Can y'all hear me?
Yeah, we can hear you.
Okay, sorry. I just want to make sure because I have recorded where I couldn't be heard or couldn't be seen and stuff. So I want to make sure before I start recording that everything is okay. Rocio, welcome. Nice to see you
Hi,
again. Hi.
good morning.
Good morning.
I was typing in the search bar instead of the chat.
Oh, okay. Okay. Well, Rocio, this is Jacob.
How you doing?
Hi, Jacob. Good. How are you?
Hey, I have to forewarn you. Like I asked a lot of questions.
That's fine. That's good.
You're still looking for a lab partner, Jacob? You
Oh
can
yeah.
ask her.
Hey, you need to be a lab partner.
I would take a lab partner. Yeah.
All right.
Okay.
I'll shoot you my email.
Y'all
Okay.
can connect through what is it called, eCampus or whatever. So
Okay.
yeah, you're welcome. I figured if I recommended you to each other, then you can, y'all can talk. But okay, so we will go ahead and start. I'm only gonna be going for an hour, so just in case I forget, can somebody let me know around 12:30 ish? I will be stopping. I don't want to go all the way through this time for the first lesson. I do have a meeting to go to right after. Do not panic about the deadline. I do have the deadlines written there because I do have to provide some deadlines to the assignments. As far as the assignments are concerned, you will work up until the point where we stop. So go on the homework, try the problems, and then whatever we haven't covered yet, we'll cover on Tuesday, and then you can go ahead and finish your assignment. The assignments will not disappear. They'll always be available. Y'all know you've been with me in 1411, right? You know how this works.
Yes.
So yeah, we'll continue with our pace, a pace that works for us, even though I do have deadlines. Those classes, I mean, sorry, not classes. The assignments will still be available. So let's go ahead and start. I want to start with this chapter. So 1411, I know for some of you that was a long time ago. We actually covered gases. That was the last chapter we covered, chapter 10, gases. So we pick up where we left off, talking about liquids, solids, and intermolecular forces. So real quick, when we talked about gases in 1411, we talked about the behavior of gas and how this behavior of the gas, let me make sure I am recording. I think I did press record. Yeah, looks like I'm recording. Yeah, behavior of the gas being tied to the intermolecular force. So behavior of gas tied to intermolecular force. Now, we did say before that gases does not really have intermolecular force. As we study liquids and solids, we'll see how the intermolecular force that they actually have influences the behavior. Okay, so we'll start with this. Bottom line, structure determines properties. This is the bottom line of chemistry. We believe that the structure of a chemical influences or determines the properties that we see in a chemical. For that reason, we want to see not only the elements available, but we want to see how they're connected, because the elements and the way they're connected ultimately produce a structure, right? And we just said structure influences property. Okay, so the intermolecular force we see in liquids and in in liquids and in solids will actually influence their behavior. Remember, intermolecular force are the attractive force that exists between all molecules and atoms. So we're talking about intermolecular force not intramolecular force. Just in case you're wondering what's the difference. So, yeah, I am erasing. And if you're wondering if you missed what I wrote when you're watching the video, just rewind. Oh, sorry. I keep saying rewind, y'all. Excuse me. Different time. When I say rewind, I mean just scroll back, right? If you've ever used a cassette tape, you have an idea what I'm talking about. If you haven't, just ignore the words. Rewind just means go back and then you just scroll back, right? My bad. I keep using the term rewind. Such is life. Anyway, intermolecular forces are different from intramolecular forces. These are forces of attraction from one molecule. So you have a whole molecule. I'm going to draw it as a circle and how it attracts another molecule. So it's not the force that makes the molecule, but it's the force that exists once the molecule is made. So when molecules attract each other, it influences whether we have a solid, a liquid, or a gas. Remember where I started, right? Gases have no intermolecular force. Liquids and solids do. So we're trying to see how this force here that attracts the two molecules influences the behavior. Okay? So once again, all molecules and all atoms have attractive forces, especially the ones that are in liquids and solids. So it's stated again down here, intermolecular forces are the forces that holds liquids and solids together. Remember, gases are left out because gases do not have intermolecular forces. Technically, they do. It's just very small, so we pretend they don't. If it's so insignificant, why even bother measuring it, right? So relatively, it's very small. So it says the intermolecular force is responsible for the very existence of condensed phase of matter, which is intermolecular forces makes it possible for us to have liquids and solids. Okay? So we saw the three phases of matter and we only studied three, solids, liquids, and gases. And remember, the existence of this state depends on the intermolecular force. Then at some point, we'll look at how intermolecular force is influenced by temperature. Okay, so instead of just saying temperature, they call it thermal energy. So apparently, when the temperature is high, we see that matter tends to exist as a gas. When temperature is low, it tends to be either a liquid or a solid. So most of the time when we see liquids as solid, if the natural state of the element or the compound is liquid or solid, if you increase the temperature and you increase it high enough, it will most likely become a gas. Okay? So we will talk about the transition going from liquid to solid and vice versa later on. This is just the intro part. So as we review the properties of the states of matter, remember state or phase is the same description. When they say three phases, but then they talk about state, you can use the word phase or state. It talks about the same thing. We're talking about gas, liquid, and solid. So I will talk about the two extremes, and then of course, the liquid will be right in the middle of the two. As far as intermolecular force is concerned, so they kind of went through the characteristic and then they put the intermolecular force towards the end. I want to flip it around and start with the intermolecular force because technically the behavior we see here is because of the intermolecular force. So I want us to talk about the cause and then the effect. So gases are seen to have little to no intermolecular force. What does that mean? When you look at gas molecules, let me try to get some space down here. When you look at gas molecules, so we're going to draw gas here, the molecules tend to be very far from each other, not influencing each other at all. They're moving very fast. They're very far from each other. The space between them is very high. So we said no intermolecular force. So I'm going to abbreviate this into IMF. This is not the monetary fund, International Monetary Fund, that lends people money. That's not that. This is just intermolecular force. So no intermolecular force. As a result of that, you see all the space available. There's a lot of space between the molecules because they have no intermolecular force. They don't attract each other or force each other to stay close together. For that reason, number one, we see low density. The molecules are not very packed together. They're free to move. Okay, they had density here. What is it? What the molecules gain in freedom, they lose in defining their shape. So they don't have no distinct shape. So these molecules, they rely on container. What they give up because they got their freedom to move around and have no intermolecular force, no force of attraction holding them back. Where they got in that, they gave up essentially the right or the ability to define their own shape. So they have to rely on the container. Whatever the shape of the container is, the molecule will adapt to that shape. And then the other thing we see with gas molecules, they tend to spread around and occupy all the available space in the container, right? They just spread around. So no distinct shape, and then no distinct volume. They can't define their own volume. They can't define their own shape. They continue to rely on container. Okay, whatever the volume of the container is, that's the volume of the gas. And in Gen Chem 1, when we're talking about, oh, the gas is in a certain container and the container is 1 liter, we just assumed that was the volume of the gas based on this property right here. Okay. What else? Yeah, so we discussed shape, volume, and density. I want to stick with what they're discussing. Okay, when it comes to liquids, oh, let me go the other extreme. Let me look at solids. Now remember, when it comes to motion here, these particles are moving very fast. So let me add one more section here. These particles are moving very fast. In my other class I just had, my non-majors class, we discussed the motion. So I'm trying to make sure I don't confuse the classes, right? Because it's all chemistry, same content, just different levels. Okay, solids are the other extreme. With solid particles, these solid particles have no freedom. Talk about a lack of freedom. The particles are smooshed very close together. There's not a lot of space between the particles. For that reason, when it comes to density, these tend to have the highest density possible because you have a lot of particles packed in a very small space. Because they have, oh, I forgot to mention, these also have the highest intermolecular force. These particles attract each other so much they don't have freedom to move around and do whatever they want. They have the least amount of freedom per particle. Highest intermolecular force of attraction, highest density. As a result of what they give up in freedom of motion, what they have is they get to define their own shape. Definite shape. They have their own shape. A solid always has the same shape at all times unless you do something to it, like increase the temperature. Number 3, they have a definite volume. They don't need the container to define their volume. They have their own volume. Okay. Now they gave up something to get that opportunity, right? The molecules gave up their freedom by being bound with the intermolecular force, but they got to define their own volume. Okay, what else? Finally, do solid molecules move? Yes, solid molecules actually vibrate. They vibrate in space, in place, I would say, vibrate in place. What that means is the molecules are not sliding past each other or floating around in the air like gas molecules do, but they are stuck in place due to the intermolecular force, vibrating like shivering. Okay. And then after we see all that, the gas molecule is right in the middle. Sorry, the liquid molecule is intermediate, right? So with liquid, everything is intermediate. Liquid. So liquid, the particles are not as far as gases or as close as solids. We have something in between. Actually, something more in between than that. Let me draw them a lot closer. So the arrangement here is not ordered, okay? So here we have intermediate, which means in between. Intermolecular force. Okay, because they have enough intermolecular force, what liquids are able to do is, as far as the density is concerned, they have an intermediate density. So I'll say intermediate density in between gases and liquids. I mean, gases and solids. And then number two, we have liquids don't have enough intermolecular force to have their own shape. When you pour a liquid, it just spreads out into whatever space is available, right? So their intermolecular force allows them to have their own volume, but not their own shape. So they still have to rely. So no definite shape. They still have to rely on container. But they have their own volume. So liquids do not spread around to occupy all the space available. They get to define their own volume. So they have a definite volume. They got that much, right? So they have definite volume. And then as far as their motion is concerned, liquids tend to slide past each other. So I'll say here, slide past each other. And for that reason, liquids can be poured. I remember when I was in school, this was like one of those trick questions. Can you pour a solid? I'm like, yeah. I had a container that had a solid in it, and I poured, I acted like I was pouring the solid, and it came out. I mean, it flopped, but it came out. But the answer was no, because only liquid molecules can slide past each other. That was a trick question because this part here was not made clear. I did not appreciate that. So I tell you guys up front, liquid molecules are the only ones that can slide past each other, making them the ones that can be poured. You can't pour a gas because the molecules don't slide past each other. Okay. Okay, so now I've kind of veered off and written all that. You can see that here. So relatively, the liquid density is more like an intermediate, because remember, it's all about space, right? But you've seen the three different levels: indefinite, indefinite, definite, and then intermolecular forces. So after seeing all that, we're now moving to how we go from one state to another. So it says phase changes or state changes. Remember, this is referring to liquid, solid, liquid, or gas. Okay. So we're seeing that the solids on the left, liquid in the middle, gas on the right. You can see how they're very different. You see how the solid molecules here are very ordered and packed together and very organized, right? Versus the liquids are close, they're relatively close together, but not organized. While the gaseous molecules are far apart, and then you see that shadow behind the molecule, it shows you they're moving very fast, right? Intermolecular forces. How do you go from one state to another? We're told if you want to go from solid to liquid to gas, as it shows right here, just increase the heat. So when you increase the heat, the observation is eventually the solid will become liquid. You keep increasing the heat, the liquid will become a gas. Okay? When it comes between liquid and gas, they show you two things that could happen. You can increase the heat, so either heat it up, increase heat, or reduce pressure. So apparently, if you increase the pressure on the gas, it actually forms liquid. Pressurizing gas forms liquid, right? So if you want to go the reverse path, you just either cool the gas a lot to make a liquid, or increase the pressure, external pressure, push the molecules close together, make the molecules attract each other, force that to happen. As a scientist, you can do that. When you do that, you form a liquid, but then you cannot push on a liquid enough to form a solid. The best way to form a solid from a liquid is by cooling. Okay? So here's the question. Why does applying heat make the molecules spread out away from each other? Before I go on and on and on, y'all had Gen Chem 1, right? So you have some chemistry from way back then. I'll just say way back when. Okay. How does the temperature influence the spacing in the molecules? Can anybody share what your thoughts are? So temperature influences, if I can spell, distance between particles, whatever they are, molecules, compounds, atoms. Feel free to type your answer in the chat box, message box, whatever, or you can say it if you want to say it. What are your thoughts? How is heat causing the molecules to move away from each other? Because that's really what's happening if you look at it from the point of view of space. Any thoughts? Okay, let me try to examine that. When you say expand, because you see there's words that you wrote and then there's words that I understand, right? When you say expand, do you mean that it went from this size to this size? Aha. Okay, what do you mean? You mean spread out? Okay, when people say expand, I know what they're trying to communicate, but this is what I think, because that's what, it gets bigger. Right. So the molecules are somehow spreading apart from each other, right? They're kind of spacing out as a result of the heat. Thank you, Sam. Sam, is that okay? Okay. So thank you. As far as the intermolecular force of attraction is concerned, intermolecular force of attraction is what keeps the molecules together. That's what keeps this happening. So if they're spreading apart, that means the heat actually breaks the force. So I'm going to give you a bottom line here. Temperature does influence the distance between the particles because temperature breaks the molecular forces, therefore releasing the molecules. So now the molecules are not so close together because temperature has separated them. And the more temperature you apply to separate the molecules, the more separate the molecules. So before we even continue with the chapter, I want us to apply what we have learned, right? Because we have learned something. Apparently, temperature breaks the intermolecular forces, causing the molecules to separate. So we are going to look at a hypothetical situation. Let's say I apply 10 kilojoules, this is a made up number, of heat to make this solid become this liquid, right? How many kilojoules of heat do you think? And the value doesn't matter so much. All I want to know is, do we need more heat or less heat to go from a liquid to a gas? So you tell me what you think I should put there in the number. How much heat will I need to take the liquid and make it a gas?
Probably increase it by 10.
So when you say, y'all use these words, okay, when you say increase it by 10, should I say another 10 here, or do you mean 20?
Add another 10.
So just 10 like that?
Yes, because you already have 10 kilojoules, and then you add another one, so that'll be a total of 20 automatically.
Okay. Okay, 20 from here to here.
Yes.
Okay. Anybody else wanna add to that answer, or are y'all just fine with that answer? Do y'all endorse that answer? Remember, the amount of heat added determines the amount of space. So I'm trying to add to the information that we know. The amount of heat added relates to the amount of space created between the molecules. So do you want to stick with that answer, 10 kilojoules, or do you want to add more to it? Think about it. Okay. I was about to say, what is that? Okay. So 10 kilojoules. Okay, here. Anybody else? Last chance. This is y'all's last chance. You want to add a little bit more. Let me tell you why. Let's say 15 kilojoules. Look at the amount of space created here. It's way more than the amount of space that was created here. The molecules went from being very organized and very tight together. Here, it's not as organized, but they're still kind of close to each other. The space created between the molecules here is so much more that additional heat has to be added. Okay? So remember, amount of heat, I'm trying to paraphrase it so y'all can see the relationship. Amount of heat added relates to space created. Did you have a comment or a question? Since a lot of space is being created, you have to add more heat. When we went from here to here, you can't just, if you add the same amount of heat, the particles will still be a lot closer to each other, right? So, and we'll see that later on. They'll talk about it towards the end of the chapter, but I'm just trying to bring this in right now. Okay. The heat it takes to vaporize a molecule is more than the heat it takes to melt it. Any questions? Comments? Okay. So now we're looking at this. They're trying to get us to connect concepts. Okay. This molecular diagram shows a sample of liquid water. I'm assuming it's the one on the right, right? So it says here, which of these diagrams, the ones below, best depicts the vapor emitted from the pot of boiling water? Okay, so this is liquid water, so that was important. I will label that liquid water. And then they're asking you which of these three is vapor. So if we're talking about vapor, vapor is gas, right? So what we're looking at here is a physical change. In other words, the other way of looking at this question, they're just saying liquid became gas. Which of these pictures down here shows gas? What do you guys say? We have choices, A, B, or C.
A.
A. What do the rest of you think? Why is B and C not correct? A is correct, right? But why is B and C not correct?
Because it completely broke down the molecule, and that's not like
I mean, you're right at everything, Jacob. Okay, you're right. You're right. So A is correct. I just want to make sure that the others also have a chance to answer, okay?
okay. I
But
said
thank you. Yeah. Thanks. Exactly. This is a physical change. Okay, for the rest of you, if you want to work together in the lab, just make sure you're actually both contributing towards the lab. Jacob and Rocio came in early, so they were asking me about the lab, right? So for the rest of you, if you want to work with somebody, do so, but just make sure everybody is contributing towards the lab and one person isn't doing all the work, okay? Then make sure when you're writing the lab report, you're writing your own words, not just copying from somebody else, because when you do that, it's a mindless exercise and you're getting zero benefit from it, okay? Yeah, funny. Okay, so yes, from the picture to here, you have a physical change, and all you have is a change in the space, right? These B and C, that would be a chemical change because it rearranged the atoms completely. Okay, very good, guys. So now it's saying here, apparently, the attractive forces that hold matter together in a condensed phase. Now we're looking at liquids and solids. I mentioned this before, right? So by now it looks like a review. All attractive forces between particles are electrostatic in nature, right? Meaning when they say electrostatic here, they just mean essentially opposites attract, right? Okay. So we're told that the strength of the attractions between particles of a substance determine the state. Gas, liquid, solid. I said that before. Now it's a review. At room temperature, moderate to strong attractive forces result in materials being solid or liquids. If you have very strong attractive forces, most of the time you have a solid. So there are times where they will write to you and say, a chemical has strong attractive forces. At that point, it's okay for you to think they must be talking about a solid, most likely a solid or a very dense liquid. Okay? The stronger the attractive forces are, the higher the boiling point of the liquid and the melting point the solid will be. So before I continue this, I want to unpack this statement here because this statement is kind of heavy. Okay? So since you the scientists are applying heat to actually melt the molecules, the stronger the attractive forces, the more heat you have to apply. So later on we'll be looking at this. Actually, yeah, we'll be looking at this later on, so I won't even do that right now. I want us to actually make progress in the slides. So the greater intermolecular force, the higher heat is required to melt or boil. Okay? So we're told the attractive forces depend on the kind of particle. So I want to go ahead and move on to that. Okay? Uh, Jacob, can you mute your mic until you're ready to speak? Sorry, because I kind of hear a lot of feedback in the background. I think that may affect the recording. Thank you. When you're about to speak, then you can go ahead and turn it on. Sorry, it's just,
No, I'm
it's,
sorry. I didn't realize it.
yeah. Okay, thank you. Boiling water requires enough added energy to overcome all attractive forces between particles, right? We're told that even though you're boiling, you're going from liquid to gas, you do have to apply enough energy to overcome all the attractive forces between the particles. But the amount of energy you're applying does not break the covalent bonds. That's why liquid water will remain as water molecule when it becomes a gas. That's just what it means. Okay? Once again, this is restated. The higher the normal boiling point of a liquid, that means the intermolecular forces were strong. So let's go ahead and figure out what are these forces. So number one, we're trying to answer this question. Why are molecules attracted to each other? Intermolecular attractions are due to attractive forces between opposite charges. That's why they said it was electrostatic, right? Positive and negative charge in the molecule. So if something happens in the molecule to create the opposite charges, as long as these charges exist, like they say, opposites will attract. Okay? So in general, we're being told if a molecule has a positive end, and we talked about this in 1411, right? If you've forgotten about it, we're reviewing it here. If you have a molecule that's polar, you know the globe, the world is polar, right? We have a north pole and a south pole. When it comes to a molecule, when a molecule is polar, that just means if this is a molecule, an area in the molecule has a positive charge, another area in the molecule has a negative charge. It has an area in the molecule that's a concentrated charge. You have a lot of positive charge. The other area has a lot of negative charge. When you have that and you have a positive end, a fixed end that's positive, the other end being negative, you then have what is called dipole. Okay? We will look at nonpolar molecules. In 1411, we covered nonpolar molecules, the ones that did not have a fixed dipole. They may have instantaneous. Sometimes they have some charges, but then the charges disappear. The charges are not permanent. Those are called nonpolar molecules. These have instantaneous dipoles. Okay. Bottom line, we're being told if you have a larger charge and the charges are actually large charge would be like +2 charge or +3 charge, or you just have more positive particles in the molecule, you have a stronger attraction. So I want to go over and talk about the major types of intermolecular attractions we will be discussing, such as London dispersion force, dipole-dipole, and hydrogen bond. So they're kind of working us towards that. Okay, so the larger the charge, the stronger the attraction, and the more permanent the charge, the stronger the attraction. If for some reason you have a longer distance between the charge, that creates a weaker attraction. Okay, so let's go to the first type of intermolecular attraction, which we'll call dispersion force. Okay, this is called London dispersion force, or the other name for that is van der Waals. Okay, different groups of chemists use different terminology. Sometimes in organic chemistry, you see van der Waals, they're referring to the same thing. Or some will just call it dispersion force. So remember, these are describing the same type of molecule. London dispersion force or van der Waals forces are seen in molecules that are non-polar. So non-polar molecules display London dispersion force. Okay, I know some of you had Gen Chem 1 last semester. Some of you had it maybe last year. I mean, last semester was last year. I mean, like in spring or maybe 2019. So I'm going to review how we determine a polar molecule. There's so many different ways of figuring it out, but I tend to stick with a non-mathematical way because I don't know what math all of you guys have had. Okay, so non-polar molecules tend to display London dispersion force. Okay, not only that, this is the only force they have. So how can we tell a molecule is nonpolar? And then when I'm done defining that, we'll come back and look at the temporary polarity. Okay, how can we tell a molecule is nonpolar? So let me segue, detour, and go back to 1411. There's so many different ways of figuring out if a molecule is nonpolar. If you're very strong in math, you can, or physics, you can use vector diagrams. And if you have a resultant force after you map out the vectors going from the least electronegative to the most electronegative, if you get a resultant force after adding up all your vectors, then you have a polar molecule. The other way that I tend to focus on is by drawing Lewis structure. So number one, draw your Lewis structure. So I'm going to give you guys two examples. One of CH4 and then one of CH3Cl. Why not? That. Okay? These are very similar. Methane and then chloromethane. Lewis structure. So I'll draw my Lewis structure 1411. So how do we do Lewis structures 1411? Carbon. So I'm drawing it for this one here, CH4. Carbon is in group what? 4. So carbon brings in 4 valence electrons, right? Times, in this formula here, I have 1 carbon, so 4 valence electrons from carbon. Each hydrogen brings in 1 valence electron. From this structure here, I do have 4 hydrogens, so we end up with 8 electrons total. We are drawing our Lewis structure with 8 electrons. We got carbon in the middle, surrounded by hydrogen, 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 and hydrogen. Oh, my bad. I skipped a step. Right? So you draw your central atom, draw your surrounding atoms, and then you fill in the bonds. Remember, for the 8 electrons, you're going to draw a bond between the central atom and the surrounding atom. The central atom can never be hydrogen. The central atom tends to be the least of the atoms present. So if you have 1 carbon and many hydrogens, the carbon will be the central atom. The central atom tends to also be the least electronegative. So if you have fewer of those elements, the element is most likely central. If it's not very electronegative, it's central atom. If it's not hydrogen, it's most likely central atom. Okay? After you have your central atom and your surrounding atoms, then you form single bonds between them, right? Each single bond uses up 2 electrons. So single bond, single bond, single bond. I have 4 single bonds, 4 times 2. That means I used up all my 8 electrons, and this we're out. Okay, being out of electrons, each hydrogen follows the Dewar rule. I have 2 electrons each. Each bond essentially is 2 electrons, so the carbon has got 8 electrons, right? So this is my correct Lewis structure. On the right here, I have CH3. What was my other element? Oh, Cl, chlorine. So carbon again, 4 times 1 is 4. Hydrogen, I have 3 this time. 1 times 3 is 3. And then chlorine is what? In group 7? 7 times 1 is 7. Now we do the math. Okay, I am going to tell you this, and I'm not even ashamed. I'm going to use a calculator. When I do all that chemistry, my brain gets fried with math. Okay, I think I have 14 here, right? When I'm working on this, for those of y'all who have had me, you know you need to do the work to check to make sure we balance each other out. For those of you who are new to this class, when I'm working on this stuff, instead of just watching what I'm doing, go ahead and work out your own so we can make sure, because I rely on your answers just like you rely on my answers, right? So I have 4 plus 3 plus 7, I have 14. Okay, I get to work with 14 electrons this time. Carbon in the middle, hydrogen is never in the middle, so I'm going to put them around here. And then chlorine is going to be on the side. Between carbon and chlorine, carbon is less electronegative. So on all counts, carbon will be in the middle. I draw single bonds. 1, 2, 3, 4. 4 single bonds. 4 times 2 is what? 8. So when you subtract the number of electrons you had, or the ones that you're using from the ones that you had, I'm left with 6, right? The remaining 6 electrons go on chlorine. Sorry, 1, 2, 3, 4, 5, 6. So minus 6, 0. We're out, right? The hydrogens look good. They tend to only handle 2 electrons. Carbon handles 8 electrons. Carbon gets to 8 electrons via the 4 bonds, and then chlorine has 8 electrons, 6 from the dots, 1 from the bond. Okay, so I'm just reviewing that quick because 1411 has been a while ago. Now let's talk about polarity. When you're judging 2 molecules to figure out if they're polar, what you're looking for is the surrounding elements, right? So look at surrounding elements. We're looking at surrounding elements, and we're making a judgment. Number 1, are elements the same? I guess I should ask, are all elements the same? If yes, molecule may be non-polar. Okay, there's one more test I have to look at. Number 2, is there a lone pair of electrons on central atom? It has to be central atom. Okay, is there a lone pair on central atom? If no molecule is non-polar. Okay, so bottom line, to be non-polar, molecule must have the same surrounding electron groups and elements. That's the bottom line. Elements, if I can spell. Okay. So based on my definition and the time I have spent to explain what nonpolar is, so look at nonpolar as non-difference. You can look at it that way. Non-difference, like there's no difference. So if the surrounding group around the central atom is all alike, all the bonds are all alike, everything is alike, and so there's no difference, then that's nonpolar. Okay? So based on what we just defined, what can you say about these two groups or these two formulas, these two molecules? Which one is the one on the left polar or nonpolar?
That one is non-polar.
Nonpolar, right?
Correct.
No difference, nonpolar. By default, the one on the right is going to be polar. Why? I usually say one of these things is not like the other.
Correct.
Based on the way the bonds are arranged, you have a resultant force. So essentially, all these surrounding elements are pulling on the central atom, well, except for these. Chlorine pulls electrons away from the central atom and therefore creates a polar situation. So the part of the molecule that will be negative, because remember, polar means you have two charges, positive and negative. The part of the molecule that will be negative will be the one that's more electronegative. Back to 1411. Electronegative elements tend to be closest to fluorine because fluorine is most electronegative with electronegativity of 4.0, like the GPA, right? So if the element is close to fluorine, it's most likely more electronegative than everything else. So chlorine is literally a family member of fluorine, right? So this one here will get that partial negative sign, and then since it's bound directly to carbon, this would be partial positive. So I like that chemists assign negative to something that's electronegative, right? That really helps. Yeah. So back to what we were looking at. I know we detour, but we have to, if we don't understand that what we are reading here will make zero sense. So in molecules like CH4, this one here, since there is no partial negative or partial positive because it's nonpolar, right? We said it was nonpolar. What we end up seeing is something called a temporal polarity or temporal dipole that's made. So essentially, electrons are constantly moving around. Within the bond, they're moving around in here. We can't see, but they're moving around in here in experiments. We see that in experiments. And they're moving around in the molecule. So sometimes the electrons end up on one corner of the molecule. And when that happens, this is called an equal electron distribution. So imagine the molecule CH4 had this shape right here. And for whatever reason, something happened to where all the negative electrons, negative charge, end up on one end. So they're like right here. As a result, the other end, the extreme opposite end, will have the positive charge. This usually happens instantaneously, like in an instant, and then it corrects itself. Then it happens again, then it corrects itself. Kind of like a flickering of the light. It flickers on and off. So it's instantaneous, so quick, and then it's on, off, on, off. When this happens, for a small instant, the left side will be partially negative, the right side will be partially positive. But this is not permanent. What we see here, this is permanent. So when that happens in the nonpolar molecules, these nonpolar molecules actually attract each other. So let me go ahead and skip over to the slide where it explains all that stuff here. Dispersion force. It says fluctuation of electron distribution within the atom results in a temporal dipole. Very, very quick. And when this happens, the side I showed you guys where you have a lot of extra electrons will then become negative. Partial negative means this. The other side that is now missing its electrons because they're on the opposite end, the wrong end, these now become partial positive. Well, when this happens in molecules that are laying side by side, let me draw them like this. This is negative, partial negative. This is positive, partial positive. The molecule that starts this situation then induces a similar effect in the next molecule. But when it does that, it actually influences the next molecule to have the opposite charge, right? The electrons that happen here actually repel the electrons in the next molecule, the neighboring molecule, causing this to be positive and this to be negative. And this happens over and over again. So you have positive, negative, kind of a flip-flop situation. In the end, guys, what we have is temporal dipoles created throughout the whole molecule. So if all of this stuff seems like a lot, what you need to remember is molecules that we consider to have no charges technically have charges, but the charges are not fixed. They're like a flicker of light. They're on and off and on and off and on and off. But that's what causes these molecules to attract each other. The force of attraction formed in this situation is called London dispersion force or dispersion force. So attractive forces caused by these temporal dipoles are dispersion force. Here's the thing. I mentioned to you that non-polar molecules have this force. Polar molecules also have this force. Okay? So here's the other statement I want to add. Non-polar molecules and polar molecules have dispersion force. Okay? So the issue we see ultimately is that polar molecules have additional forces. So in the end, we'll actually see the difference between the polar molecules and non-polar molecules. So what I explained earlier, they show it to you here in the picture form. I won't go over that again because I drew my own pictures. They weren't the best, but they did the job, right? So this is showing you how one molecule influences the next, and they call this inducing. One molecule makes the other molecule have a temporary dipole, and then before you know it, the effect spreads around. It's like it goes viral. Okay, they're giving you examples here of molecules that have dispersion force, and apparently not only do molecules have dispersion forces, but the size of the molecule makes a difference on the magnitude, how big that force is. So we're told here, effect of molecular size on this size of the dispersion force. Before I go into that, I want to talk about examples, right? So let me give you here examples of elements or molecules, because I didn't do that, that have London dispersion force only. I want to focus on the ones that have London dispersion force only. So I'll focus on non-polar. Okay. I gave you example, CH4. That was one example. CO2. When you draw the lowest structure, you will see why. The surrounding groups are exactly the same. What else? PCl5, etc. for the compounds. For the elements that exist by themselves, for example, noble gas elements, helium, neon, etc., etc. Okay? These tend to be nonpolar. They're only forming a compound in its place. Now, once you see the example, the next thing I want us to see, within the nonpolar molecules, do they all have the same level of intermolecular force? The answer is no. Some are stronger, some are weaker. So how can we tell the difference? The first difference they tell us is molecular size or the molar mass. So as the molar mass increases, the number of electrons increases. And because you have more electrons, you have more polarizability. So polarizing is, if you want a visual, polarizing will be like having, if people were electrons, so if you had people in a room, right? So you have people spread out in a room, and then they were spread out evenly, you would say this is non-polarized because they're evenly spread out in the room. If you did something to cause everybody to go in one corner of the room, then that room immediately becomes polarized because everyone is in one corner and the other corner is now blank. So this, we go from polarized, spread out evenly. We go from non-polarized, spread out evenly, to polarized, not spread out evenly. Okay. Polarized just means you have all the electrons in one corner of the molecule. So more electrons, more polarizability. Okay. And if you have more electrons, you have a greater strength of the attractive forces because the partial negative becomes even bigger because it's influenced by the number of electrons. Partial positive also becomes bigger. Okay? So the example they say here, besides the example I gave, is once again, if you have increase in mass results in increase in intermolecular force. So they should give us an example down here. Oh, yep, there it is. So helium is the smallest of all the noble gas elements we have, right? Helium is the smallest. They give you the mass here. It's only about 4 grams per mole. Xenon is the largest, 131 grams per mole. So what is missing here is a table of intermolecular force. Based on the mass, we can say this has the lowest London dispersion force, right? Based on the mass, we can say xenon has the highest London dispersion force. Because remember they told you the number of electrons affects strength of intermolecular force. So if you have a greater mass, you have more electrons. The more electrons you have, the more intermolecular force you have. So I need to ask this. What has the London dispersion force? How does this relate to the boiling point? What do you all think? When you're boiling, what exactly are you doing? How does the London dispersion force being very high influence the magnitude or the size of the boiling point? Any thoughts? Don't worry about your answer being right. I just want somebody else to talk besides me. So we're saying xenon has a very high, well, of the group, right? Because in chemistry, we're just doing a lot of relative comparison. Of the group we have, xenon has a very high London dispersion force because it has a very high mass. But what does that have to do with the boiling point? When we are boiling, what are we trying to do?
We're trying to increase the pressure so we could break it down, correct?
We're not trying to increase the pressure, but we're increasing the temperature.
There you go.
Okay, so you are remembering that slide, right? That had pressure and temperature,
Yes.
right? When you're boiling, you're increasing the temperature, and the temperature breaks the London dispersion force. So if you think of the London dispersion force as a barrier, something you're trying to overcome. If the LDF is high and you are trying to overcome it, you need to show up with more heat. So if this is high, the boiling point has to be high. If the LDF is low in helium, the boiling point doesn't have to be as high because the target is lower, right? So boiling point, as far as the practical sense is concerned, as far as what we're talking about is concerned, when you are boiling, you're trying to break the intermolecular force. So think about it that way. I mean, boiling does have an official definition, but in the context, boiling is breaking whatever the intermolecular force is. In our context here is London dispersion force. So if the London dispersion force is very high, you need to apply more heat. If it's low, you can kind of coast with a little bit less energy, right? Okay, so let's continue here. Then they're telling you not only the molar mass matter, so does the shape of the molecule. Shape matters. So here we're seeing that we're told branch chains. So you have a molecule, they're showing you two molecules here that have the exact same mass, okay? Because essentially in the formula, this is C5H12, C5H12. Now, I'm giving you organic examples, okay? It's the same chemical formula, but the atoms are arranged differently. One of them is more linear, and then the other one is more branched. It looks more like a circle, right? So this is more branched. Okay, so we're told branched chains have lower boiling points than straight chains. Okay. So lower boiling points means you need less temperature. If you need less temperature, that means I'm trying to work backward. That means the target was less. Lower London dispersion force. Okay. That's what I understand so far based on what I read. But let's see, why is that the case? They say the straight chain isomers have more surface to surface contact. Oh, so what they're trying to say here is remember, polarizing, which creates a temporary dipole, is all about having a segregation between the charges, right? You have a negative charge on one end, doesn't really matter which end, a positive charge on the next end. And then after that happens, the one molecule influences the next molecule, right? So this has partial positive, partial negative. So if there's a great surface area of influence, then the first molecule can influence the second molecule more. So the surface area, increasing surface area, increases influence. You have more contact. Okay. When they say surface area, sir, they mean like the space for contact, right? Over here, the place where they're contacting is not that big, right here. Okay, so yeah, this is still partial negative, partial positive. They do influence each other, but not as much. Not as much as the other scenario. So in this case here, when you have more straight molecules versus the ones that look round, so straight, if I can spell, chain molecules have greater intermolecular force. Okay, so I had to conclude that. So now let me go ahead and look at this right here because there's a lot being communicated in this picture. I want to add my intermolecular force here. I remember this has a higher intermolecular force. This has a lower intermolecular force. They said a lot of things, but this is the bottom line. Okay. If it has a higher intermolecular force, does that relate to the boiling point temperature? Let me see what's going on here. Yes, the higher the intermolecular force, the more temperature you have to add to overcome those bonds and then make it boil. Here, since it has a lower intermolecular force, you don't have to apply that much temperature. So it's lower boiling point. Any questions about that? So when you're working on your homework, you see that relationship back and forth. I am looking at the time, so I'm gonna go. Let's see. I'm gonna go 10 more minutes and I'll be done. 10 more minutes. That's it. Okay. So here we're now looking at. We're moving on to dipole-dipole attractions. So this is the polar molecules. Polar molecules have number one, a London dispersion force. I mentioned that earlier. And they also have an additional force that we don't see in nonpolar molecules called dipole-dipole. These molecules are able to have what we call a permanent dipole, not one that flickers back and forth. So when you go back and look at molecular geometry around the central atom, when you compare the groups, the elements may be different or you may have a lone pair. So we're given an example here. This is acetone nail polish remover. So let me draw my lowest structure. I don't want to disrupt that picture on the left right here. Like that. This is more like a Vesper model technically. But here, and I look at this here. You can tell these two groups are alike, but this one is different. Because oxygen is different from the rest of them, that makes this polar. Polar molecules have LDF, but they also have dipole-dipole. And the dipole-dipole comes about because of the electronegativity of these two. Oxygen is always electronegative compared to carbon. So the polarity we see here is not coming on and going off and flickering back and forth. It is there all the time. So we have polarity all the time. Permanent dipole. Okay, so now we have an additional intermolecular force. So when you're trying to break the bonds in here, you have to break two bonds. To heat acetone, I don't know why you'd be heating it, but if you were to heat it, if you're planning to heat to boil, your goal is to break dipole and London dispersion force. So if that's your goal, you're going to be applying extra heat because you have extra bonds to break. Okay? So hopefully that means for you as a scientist, heating means overcoming these bonds. You're trying to break them. You don't hate them, you just have a purpose behind breaking these bonds. So to give you an example here, I mean, we just covered it. We're comparing these two molecules here, right? Formaldehyde and ethane. While I'm here, I want to give you guys an overall rule. For organic compounds that have this format, C, some number, H, some number, these are all non-polar. We don't have all rules in chemistry a lot, so when you have all rules, you want to embrace the all rules. Every time I hear all in chemistry, I'm like, yes, because I know it's rare. If you have organic compounds that have carbon and hydrogen only, they tend to all be nonpolar. Okay? At you guys' levels, nonpolar. So when I see this has this format, I'm like, okay, nonpolar. If it has another element, like this one here has a general formula CXHY because it has a carbon, right? It has a hydrogen and it has the oxygen. When it has that third element, the third element tends to make it nonpolar. So if you're the kind of person that needs to see the big picture, sorry, it makes it polar because it's different from this, right? It makes it polar. Right. That third element tends to be a electronegative element, so it introduces polarity. So bottom line here, in this slide, what we're really looking at is polar versus non-polar. Okay, that's the bottom line of the slide. They made sure they picked elements where the mass was the same. So whatever difference we're seeing, we can't blame it on the mass. So now we go to the structure. Remember I told you, regardless of what this is nonpolar. So judge this. The electronegativity between the bonds are not big enough for it to qualify for being polar. So this is going to be nonpolar. So we see this and we conclude nonpolar. Don't even waste time on it. Okay. This one here, look at your central atom. Look around it. Same, different. Polar. Okay. So before I look on the right, because this is polar, there are two forces that have to be broken. LDF, DD, London dispersion force, dipole. This is nonpolar, so all it has is London dispersion force. That's it. The minimum. It has the bare minimum. So since it only has one bond to break, which one will have the higher boiling point? The top one or the bottom one? What do you all think? Which one has a higher boiling point?
I believe it's going to be the top one.
Hold on a second, let me scroll over. Yes, guys, the top one, right? Because you have to break more. I kind of think about this. I don't know. My mind wanders a lot. I think about when they do the karate thing, and you can tell I don't do karate because I'm calling it the karate thing. When they're chopping the blocks, when you have more blocks, you have to apply more force to break those blocks, right? The blocks, the thingies, yeah. That's what I think about. More blocks, more force. So more bonds, you have to apply more heat. So when you go over here, you see that in both the boiling point and the melting point. I know that because these are essentially gases in room temperature, so it's hard to see, but technically this number is larger than the bottom number, right? Think of the number line. You have 0 and you have the numbers that go left and the numbers that go right. This one here, negative 19.5, is further right, so technically it is higher. Negative 88 is further left. If these numbers give you some level of anxiety, you can't relate to them, draw the number line. The one that's further right is higher. Okay? So this is higher because there is more to overcome. Okay. And your homework questions will kind of be like that, right? And then at some point, we're finding out not only is the boiling point slash melting point influenced by intermolecular forces, so is the solubility. Now, if you've had high school chemistry or chemistry before today, they probably said to you, like dissolves like. Okay? These catchphrase, like dissolves like, and you remember it, you memorize it, and it's great. Like what though? And they said maybe like chemicals. What do you mean like chemicals? Like a metal and water? What they meant to say when they said like dissolves like, they're talking about intermolecular forces. The more alike the intermolecular forces are, the more they will dissolve in each other. Okay, so when they say like dissolves like, nonpolar will dissolve nonpolar. Remember, nonpolar is LDF. LDF dissolves LDF. Now, there's a caveat here. Sometimes one intermolecular force dominates over the other. Okay, so all the forces are not alike. Some dominate the other. Okay, so they're saying here polar substances dissolve in polar substances. In polar substances, of course, the dominant force there is dipole-dipole, dissolves dipole-dipole. Nonpolar molecules dissolve nonpolar molecules. We just said that. Okay. So I'm not going to go into all of this. I'm just going to focus on the bottom line. So do polar dissolve nonpolar? Let me give you this example. Does water dissolve in oil or vice versa? What do y'all think? Does water dissolve in oil?
No.
Right. Very good, right? So water, let me draw a water structure real quick. Lewis structure right here from 1411. I know. Water is polar. How do I know that? Look at the surrounding groups. These two are alike, but they're different from that group. There's a lone pair on the central atom. So water is polar. Plus, in biology, they say water is polar. Then they move on. Like, what? Qualify that statement. We're done. Moved on. Right? In chemistry, we're saying this is why it's polar. Okay. Oil tends to have the general formula of this, which I told you before. It has this nonpolar region, so oil tends to be nonpolar. Sometimes, even if oil does have an OH in there, which we'll talk about later on, oil tends to have a nonpolar character. So oil is essentially nonpolar. So we said water is polar, oil is nonpolar. They don't mix each other because even though the nonpolar has LDF and the polar molecule has LDF and dipole-dipole, dipole-dipole is the more dominant intermolecular force. And so it doesn't mix with this. They don't mix. And there's more going on with hydrogen. Hydrogen actually has a third force that we haven't seen, but we'll talk about that too. So tell you here, pentane, you see that? This is nonpolar. Remember I told you guys that? Pentane is a nonpolar molecule and water is polar, so that's the example I chose here. So for that reason, they don't mix. When you try to mix them, they will not mix because the intermolecular forces are different. In the lab, even though they're both liquid, they have the same color, which is colorless, no color. When you look at them in the lab, they will actually, when you try to mix them, they'll form layers, with a dense one being on the bottom. So over here, you have H2O on the bottom, pentane on the top, C5H12 on the top, and they will not mix because the top one is more oil-like, nonpolar. The bottom one is more water-like or polar. And this is nonpolar. Okay, so they don't mix. Let me see. Oh, let's do this. Okay, for real, this is the last slide. The last slide, and then we're done, okay? When I start teaching and I just get into it and I'm like, wait, I have other responsibilities. Forget those responsibilities. Don't tell people that. Okay, this is being recorded. Sorry, where was I? Yeah, we'll look at this. I get caught up and then I I got other responsibilities. So here, let me go ahead and copy this over to the next page. I'm using this app like a pro. I'm saying that before I start making mistakes. No, I just have been using it more now. So before I was like, wait, how do I copy this over? Yeah, I'm doing a lot better now. So proud of myself. Okay, so which molecules have dipole-dipole forces, right? So they're asking you which molecule is polar. That's the question they're asking you. So as usual, draw Lewis structures, draw Lewis. I won't go through the whole process. I'll just draw it. Okay. So for this first one, I'll say, since this one here has double bonds and that part has been a while, I won't do B and C in detail. Carbon is group 4 times 1, right? Oxygen is group 6, and we have 2. So this is 4, and this is 12, right? 16. Carbon goes in the middle. We only have one carbon surrounded by 2 oxygens. Then you put a single bond here, single bond here. I used 2 bonds, 4 electrons. I'm left with 12. I'm working this out once again. 14, 11 for some of you has been a long time. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 2 is what? 12. We're out of electrons. Now we check for octet. These oxygens have octets. 6 electrons, 1 bond made 8 electrons, 8 electrons. But the carbon only has access to 4 electrons through 2 bonds. We want to get the carbon to 8 electrons. So use the electron on either side. Oops, that's the flaws of this app. Okay, I used 2 electrons from the left to make a double bond, electrons from the right to make that double bond. Now I have my CO2 molecules and I have symmetry. Okay, this now has 8 electrons. Okay, now what was I going to do again? Oh, is this polar? Let's see. I have my central atom, I have my surrounding electrons, and these are supposed to be alike. They're both oxygen. They both have 2 lone pairs, 2 sets of lone pairs, and they have 2 bonds. So these are going to be what?
Nonpolar.
Nonpolar, yes. So because they're nonpolar, they only have LDF only. Sorry. So this is not one of the answers. Okay. B. B, I'm not going to go through all the steps because this is not complicated. Carbon in the middle. Carbon usually forms 4 bonds like that. It's surrounded by 2 H's and 2 Cl's. What do y'all think? What's the verdict?
That's polar.
These are different, right? Polar. Man, I write so big. I'm going to have to open a new page. I'll do one on this side. Polar, right? So this is polar. It has LDF and it has dipole-dipole. So it has dipole-dipole. So yes to this one. We already did CH4, but I'll do it again. Just real quick over here. CH, H, H, H. What do you say about that one?
No.
Nonpolar. Yeah. So only LDF. So only B should be polar, dichloromethane. Now you learn how to name that when you take organic. If you're taking organic chemistry, if you're not, then that's just some compound, a compound called dichloro for 2 chlorines and then methane. Yep. So they go into all the words, explain all the stuff, geometry, a lot of words, and then we're here. So when we meet next week, we'll start with hydrogen bond. Start here.
Okay, so we're gonna start with the same chapter next week.
Yeah. Yeah.
Okay, all right, cool. I thought you were just gonna make us do it.
I mean, I can do a lot of things. I have the power. No, I won't do that.
Okay, cool. Thank you.
That's why I started this lesson with disclaimer. Even though we have the due dates, the assignments will not disappear. Get what you can get done this weekend, and then we'll finish this on Tuesday. Then you can continue with your homework then.
Oh, okay. All right.
What do you mean? You can finish your. Hey, okay. Let it be known, since this is being recorded, I have nothing against you working ahead. Nothing. How would I hold that against you? I can't. So if you want to work ahead, go ahead and work ahead. But since we're not done with chapter 11, is that what this is? We'll finish it on Tuesday. Then you can work on the rest of the homework.
All right.
Why are you saying what's the about?
I'm just a veteran trying to get some education in, and then like I don't. This is all new to me.
Right. So when, I mean, whatever we cover today, you want to be responsible for that, because if you don't work on that by Monday, you forget all of this. Forget Monday. By 3 o'clock today, you'll be like, what? So you want to work on this homework based on what we covered till dipole. Well, yeah, right before hydrogen bonding. And since we've covered all this, you may actually be able to read hydrogen bonding on your own and get it. You want to try that out. But I wrote myself a note to start here next week. So when I scroll through the slide, I'll see the little note to my future self. Start here. So when we meet on Tuesday next week, we're finishing this chapter. It will go a lot faster because I won't. Yeah, I think it will go a lot faster. We should be done with this on Tuesday, and then we'll continue from there.
Hey, you got a free weekend for me not harassing you.
Geez, thank you very much. I mean, what will I do with this free weekend? What will I do with myself? Go out and celebrate. Does anybody have any questions? When you go over the homework, please, so when you go over it, you probably have more questions for me next week, right? When you try to apply this. And then you see how it kind of plays out in the homework questions and the quiz. I forget y'all have a quiz too. Yeah. Other than that, we're good. I am done. So you guys have a nice weekend. I can't believe it's Thursday already. This is like Tuesday for me, but you know what? It's Thursday. So if you're having any issues with the homework, any problems with it, you can send me an email, and then I'll do what I can at that point. Okay? Okay. Have a nice weekend, y'all. I am
You too.
done.
Thank you.
Okay.
All right.
See you Tuesday.
All right. Thank you. Goodbye.
Okay. Bye.